I guess we can start now.
I see. So today is the last day of this workshop, and today two people will talk about Axion-Like particle and its probes using 21 centimeter line signal or gravitational waves. The first speaker is Professor Kenji Kadota, and he will talk about the connection between 21 centimeter physics and axion dark matter. So please.
Thank you. So today,
let me say one thing. So the talk is 30 minutes, but you can freely ask during the talk. So please start.
60 minutes, 30 minutes,
60
60 minutes.
60 minutes.
So sorry.
Okay.
1 hour.
Yeah.
Right. So today I'm going to talk about axion-like dark matter using bounding axion-like particular axion-like dark matter using the mini halos based on the work in collaboration with the former IBS postdoc Toyoka Sekiguchi, who is now at KK, and Hiroyuki Tashiro at Nagoya. Another paper in the same model, post-inflationary PQ symmetry breaking scenario with the Hayato Shimabuko. We now started the faculty in the Yunnan University in China and the Kyoto Moichiki at Nagoya. And this is the summary of my talk today. So first I'll talk about what models we have in our mind. So it's a post-inflation PQ symmetry breaking scenario. And I'm going to define what the mini halo is. I have a particular mass range for the halo I'm going to talk about today. And I'm going to make a comparison between the mini halos in action scenarios and the mini halos in no action scenarios. The bottom line is that we have more abundant mini halos in action scenarios. And then I'm going to talk about observational prospect using 20 centimeter. And the result we are going to get is using 20 centimeter, it's 10 to the minus 13 eV or so, to be compared with other current bands from CMB and Lime alpha. So way better than the current bands in the future. All right, so let me get started with what kind of scenario I have in my mind today. So it's a post-inflation PQ symmetry breaking scenario. So PQ gets broken after inflation. So once this U1 symmetry got broken, the field can be anywhere along this bottom of the Mexican hat. So angle theta can be anything between minus pi and pi. But because our current horizon is much bigger than the horizon size at that time when U1 symmetry breaking occurred. So it means in each causally disconnected patch has different angle theta. And when this Mexican hat gets tilted so that and when Hubble constant friction term becomes smaller than the mass of the action starts oscillation around the minimum. And because theta value is different in each Hubble patch, it means the height of the potential amplitude of this oscillation is different in each Hubble patch. So it means because the potential energy is amplitude squared, and the action is defined as a action decay constant, the size of the Mexican hat times theta is the action amplitude. So mass squared times action squared is just potential energy is hugely different in each patch. So it means we have a huge density fluctuation. So rho bar is a mean density, the average density, and rho A is proportional to theta square. And because it's a random number between minus pi and pi, just a white noise. So just a flat Poisson noise. Okay. So in terms of the power spectrum, which we often use in cosmology, which by definition, by integrating for whole over K space, gives this flat Poisson noise, we can expect this P of K power spectrum would be inversely proportional to K to cubic power because the volume is K to cubic power. And on top of that, we can also expect there's a cutoff in this power spectrum because inside the horizon, in the Lagrangian, there's a special gradient term. So inside the horizon, it's causally connected, so it's energetically more favorable to smooth out the fluctuation. So in in a small scale means bigger k is a wave number. So bigger k means smaller scale. So inside the oscillation scale, when action starts oscillation, the perturbation vanishes inside this horizon patch, because once it starts oscillation, it behaves like a matter, and dynamic matter domination fluctuation grows proportional to scale factor. So this gives a cutoff scale in fluctuation. So k bigger than oscillation scale horizon size, when it starts oscillation, it vanishes, and smaller than that k oscillation, it's just a white noise. So pictorially, it looks like this. I multiply by k to cubic power. So if p power spectrum is white noise flat, k to cubic power means the slope is 3. So this different color represents this additional ice curvature action perturbation depending on this cutoff scale, right? And the mini halo I'm going to talk about particularly focus on this particular mass range. In terms of k scale, the size is around 50 to 1000 megapascal inverse. So k is 1 over length scale. So inverse of k gives the size of this horizon. And of course, there's a standard adiabatic perturbation prismal from inflation. So total power spectrum, this black curve is just the standard adiabatic lambda CDM cosmology perturbation plus this ice curvature. So as you see, in a large scale, for instance, CMP scale, this ice curvature perturbation is negligible. So this action perturbation would not affect the large scale observation like CMP. And if we take a k oscillation, k cutoff large enough, then it would not affect Lyman alpha forest range either. So we can tune or we can find an interesting k cutoff, k oscillation scale, which is not sensitive to the current data, but sensitive to the future data like 21 centimeter. And we want to see this effect of additional ice curvature perturbation, which shows up at a very small scale through the mini halos. Right, so is it clear? So total perturbation is standard 1 plus ice curvature. And there's a 1-to-1 correspondence between this k oscillation and action mass, because this k oscillation starts when the action mass becomes comparable to the Hubble rate. So what observation cares about this k oscillation, but once we find out what kind of cutoff k our observation can constrain, we can translate that k cutoff to action mass. So if we look at, for instance, this time-independent action mass, so corresponds to n equals 0, the n equals 0 curve is this green one. So once we are giving some k knots, there's just 1-to-1 correspondence to MA, right? So if MA gets bigger, means oscillation starts earlier, means the horizon size are smaller, and smaller size means bigger k, so k increases, the slope is positive. I also wrote this gene scale. So gene scale basically comes from the fact that for such a light particle, like action-like particle of this such a small mass range, there's a quantum pressure. Right? If you go to very, very small scale, then from uncertainty principle, delta x small means delta p is big. So due to this so-called quantum pressure, the perturbation cannot grow, it gets the fluctuation gets erased out. So some people put a bound using this property of the quantum pressure such that the power spectrum gets suppressed if you go to very, very high k. But in my talk today, this cutoff due to genes action dark matter gene scale always bigger than the scale I'm going to talk about, mainly mini halo scale. So this cutoff due to this fuzzy nature of the dark matter, quantum pressure cutoff is not relevant in your model, in my discussion today, because that's too much scale, too small scale compared with the mini halo scale. Okay, so this is a basic picture. We try to bound this cutoff scale by looking at the effects on enhancement of the small scale structure formation. Right, so this is just overview of how this PQ symmetry breaking scenario can enhance the small scale power spectrum fluctuation of the dark matter. And let me talk about where this explicit mass range comes from. So mini halos, I'm going to talk about today is some very small halo which is packed by neutral hydrogen. And for this reason, I want this halo size to be less than 10 to 8 solar mass. Because if the mass gets bigger than 10 to 8 solar mass, the virial temperature inside the halo, the gas temperature inside the halo becomes bigger than 10 to 4 Kelvin. So if the temperature gets bigger, or if the halo size gets bigger halos can produce lots of stars inside the halo. And if there's a star formation, those stars and also early forming galaxy emit lots of energetic photons, and those photons can ionize the neutral hydrogen. So this upper bound comes from the condition that the neutral hydrogen can stay neutral. And because 20 centimeter signal I'm going to talk about in a moment comes from neutral hydrogen, not ionized hydrogen, I wanted this upper bound. So I'm going to talk about the halo, which is starless. So starless halo, which is too small to host stars and galaxies. And there's also lower bound, it's just a baryon gene scale. So baryon has some thermal velocity, and because I want to measure the 20 centimeter fluctuations. So basically it's a fluctuation of the neutral hydrogen distributions. So baryon basically means hydrogen. So if the halo is too small, if you go to too small scale, then this baryon thermal velocity erases out the baryon density fluctuations. So we want a mass cutoff so that we are bigger than the baryon gene scale. So I'm going to concentrate on this particular mass range to ensure that there's enough neutral hydrogen fluctuations, and also those neutral hydrogen can stay neutral. So pictorially, in the early stage of the universe, like latest 30s or so, there are a lot of neutral hydrogen, but a big halo, massive halos can form the star inside those halos. And then this white region represents the ionized region. So ionized region get bigger and bigger, and by redshift 6 or so, the universe becomes completely ionized. So our current universe is ionized universe. But I'm going to talk about this small halo represented by blue color, where there's a dense neutral hydrogen clouds inside this small halo. Okay, so this is why I want to stick to this particular mass range. And again, coming back to this picture of the power spectrum, people often talk about this warm dark matter which separates around this scale like galaxy size, but I'm going even smaller scale. So as I mentioned, it's a 10 to 4 to 10 to 8. So in terms of K, it's like 50 to 1,000 or so. So as I mentioned, CMB and galaxies are much bigger scale. Some people talk about in a post-inflation PQ symmetry breaking scenario, the so-called axion mini halo, that's a much smaller scale. Like even can be like 10 to minus 10 solar mass. Those are fast collapsed objects in the universe. So because there are so big fluctuations due to different angles theta in each causally disconnected patch, as those fluctuations can collapse into itself gravitationally too. So there's a very fast gravitationally collapsed objects called axion mini halos, but those are not what I'm going to talk about, because those are the scale which 20 centimeter cannot prove. This is interesting topic itself, but I'm more talking about more diffuse, much bigger halos, but which is still mini enough to host the neutral hydrogen. So this is the mass and scale I'm going to talk about today. Right? So let me give you some comparison between the mini halo abundance in action scenarios and mini halo abundance in no action scenarios. So for particular a number of k cutoff 10 to the fourth, for instance, 10 to the fourth in this figure corresponds to this blue curve. And at the redshift of 100, this y-axis represents the number of halo, number density. And in a standard lambda CDM, structure formation starts typically like redshift 20 or below. So at redshift of 100, there's no curve corresponding to lambda CDM. The curve is much, much smaller than, too small to show in this figure. But in action scenario, there's already big fluctuation from those randomly distributed theta values. At the Z100, we already have lots of halos, small scale structure already got formed. So this is number density at the redshift of 100. In hierarchical structure formation, small structure form first, and then they get merged together to form the larger halos. So at 100, there's most of the halos are in a small mass range. If we wait until Z of 10, then this blue one changed to this red dot one. So as I said, those lots of abundant mini halos, some of them get merged to form the bigger halos. So amplitude at a very, very small mass range decreases, but amplitude in a larger mass scale increases. So blue one changed to red one. If we wait until redshift of 10 or so, even no action scenario already have some structure starting formed. So this red one, red solid one is a no action case with the just standard lambda CDM. And we already see some substructure in a small mass range, but still we see this action scenario can still dominate. And if we wait to the current epoch, then most of the small one already got merged, assembled into a bigger one. So the difference in a small mass range becomes smaller and smaller. And moreover, if we wait until redshift of 10 or so, already very big, like even galaxy scale, 10 to 10 solar mass structure can form. And at that scale, the adiabatic perturbation, standard perturbation can even dominate the scavenger perturbation. So for the like 10 to 10 solar mass range, there's no distinction between no action and action case, in that it's pretty much determined by adiabatic perturbation. But if you go to very, very small scale, there's still slight increase, so dashed black and solid curve. So there's still a little bit enhancement in the number density, but it's very, very small. Because if you wait long enough, most of small structure move to the larger one by merging together. So we, by 20 centimeter, try to measure around Z of 10 or so. I'm going to talk about the 21 centimeter signal from large scale structure of the universe. So 21 centimeter signal at Z equal 0 is 0 anyway, because our universe is ionized. So this 20 centimeter needs a neutral hydrogen. We need to go to the universe where the universe has not completely ionized yet. And we know from the data like CMB, for instance, the ionization got completed by redshift of 6 or so. So we have to go to the redshift above 6 or so. But if you go to too higher redshifts, it's harder to see observation. It's easier to see if redshift is closer to us. But if it gets too close to 6, and this ionization, lots of energetic photon from the galaxy and stars is very model dependent and very messy. So we try to draw the figure at the redshift of 10-ish. And around the redshift of 10-ish, compared with no action case, this black one, we can see clear difference between action scenario and no action scenario. So for instance, if K oscillation is like 100 per megasecond divided by megaparsec, then because the ice curvature perturbation is inversely proportional to k to cubic power, in k oscillation small number means the amplitude of the ice curvature perturbation is big. So there are lots of small scale structure produced very, very early. But if they produce too early, lots of them get merged into the big halos, and it may get out of the range of our interest. It becomes too big a halo to be called some mini halo in my talk today. So this red one represents that features. For small mass range, it's much, much smaller than the abundance of the adiabatic scenario, no action scenario, so black one, red one. And for the very, very high mass range, red one is much bigger than black range. And this shaded region is the scale of the action mini halo, like 10 to the 4th to 10 to the 8th or so. So I want to see the difference between action and no action scenarios in this shaded region. If we can see the 21 centimeter signal from this red one, then there's a huge difference between black and red one, so it's easy to see, but the signal is small because amplitude of the red one is small. And if the K oscillation gets very, very big, like 10 to the 5th, then this is also a problem because the amplitude of ice curvature perturbation becomes too small. So the difference between this pink one and the black one gets smaller and smaller. So there's some optimal K, which is not too small and not too big, which is easiest to see to be proved by 20 centimeter. So it turns out to be around the 10 to the 4th or so, this blue one and black one. And by measuring the 20 centimeter signal from this K of 10 to the 4th or so, we want to see the 20 centimeter signal for the case of this blue one and black one. There's enough difference already. So this is the how mini halo abundance is affected by the ice curvature perturbation. Okay. Right.
Okay.
So yeah.
The red one is for the heavy axion case.
So K oscillation, K small,
yeah.
Cutoff is small means cutoff is big. So horizon size is big. Mm-hmm. So means action oscillation started later. So means action mass is smaller. Yeah. Right. So if action mass is heavy, means oscillation started earlier. So horizon size at the earlier time is smaller. So K is big. Is it okay?
Okay.
Yeah, okay. Right. So I'm gonna talk about how do we see it, and as I kept mentioning, I'm interested in 20 centimeter signal because this mini halo is very good because it can accommodate dense neutral hydrogen inside. And what is 20 centimeter? And one of the common place you see 20 centimeter is this galaxy rotation curve. So it's one of the indications of the existence of the dark matter. And when we measure rotation of the galaxy, we measure Doppler shift. And when the radius from the halo center is close, there are lots of stars, so we can just measure the Doppler shift from the motion of the stars. We can measure how fast the galaxy is rotating. But if you go a little bit further, there's no stars anymore. And those bigger radii parts, we're using 20 centimeter. Measuring the Doppler shift of the 20 centimeter emission from the neutral hydrogen. So this 20 centimeter emission is the hyperfine splitting. So in n equal 1 ground state, there's a small energy split between the spin parallel and the spin anti-parallel. And at the rest frame, it's just exact wavelength, emitted wavelength is 20 centimeter. And it's around gigahertz. So it's a radio frequency. The radio telescope on the Earth can measure it. You are probably more familiar with the Lyman transition or some other higher one. They are transition between different energy level. 20 centimeter is within n equal 1, but the parallel and anti-parallel of the spin of the electron and the proton. So that's why I want to talk about neutral hydrogen, because it gets separated out, it gets ionized, there's no interaction between spins. So I want a neutral hydrogen. And this transition is very, very small energy split, like a micro EV split energy level. So you can never measure it in a lab unless you wait for like age of the universe. But we can measure it from the sky because neutral hydrogen is the most abundant element of the universe. So even though this transition rate from one single neutral hydrogen takes so long time because we have so many of them in the sky, we can measure it. As I said, I'm gonna talk about the signal from the whole sky. So 20 centimeter signal is 0 in ionized universe. So I want to go to a little bit higher redshift where universe are still neutral or partially neutral. And radio telescope is good because those radio signals can go through the Earth's atmosphere. So we don't need a satellite. We can do it on the Earth. It's only visible wavelengths and radio wavelengths which can go through the Earth's atmosphere. So it's nice to be able to do it on the Earth. And also advantage compared with optical telescope is a radio telescope can do it basically for 24 hours. Night or daytime doesn't matter. And in signal to noise estimation, we assume the SK-like experiments. The construction is supposed to start this year, but because of this pandemic, I heard the construction will start next year. And this is a huge telescope, literally thousands of them, like big dish antenna and also dipole antenna in Australia. And this is really big data science. LHC and SK made an official agreement for big data science agreements. LHC has like 200 petabytes in a hard drive now, but SK is supposed to deal with like 300 petabytes every single year. So it's a huge data. So it's good to have a huge data, but we have to figure out how to deal with such a big data. But this is just to give you some impressions that this radio telescope can be a good probe to study not only cosmology, but also like particle physics, like action in a very, very small scale. But the problem with those is because radio waves is pretty common, there are lots of foregrounds from galaxies and even human devices can interfere your radio experiments. So this map represents the radio map of the Earth by the human activity, like your smartphone, FM radio can interfere. So the reason why we still have not found 20 centimeter from the large scale is because we have to deal with foregrounds. Like for instance, H's results a few years ago, still under hot debate regarding the how to deal with the foregrounds. So we have to deal with lots of foregrounds, but I think the science we can get out of this 20 centimeter signal is huge. So I think it's worth seeking the possibility to use 20 centimeter to study some particle physics model, like axion physics. And just to give you a more impression about how useful 20 centimeter can be, this is just CMB power spectrum, and this is 21 centimeter power spectrum. As I said, 20 centimeter can probe much smaller scale than CMB or galaxy scale. CMB power spectrum gets suppressed once we go to the angular scale, small scale, which corresponds to the thickness of the scattered surface, because CMB photon gets diffused inside the finite thickness of the CMB last scattering, which was not instantaneous, so it was around megaparsec or 10 megaparsec scale. So CMB photon fluctuation gets diffused. So this so-called Silk damping is the limit for how small CMB observation can measure. And compared with this CMB damping, 20 centimeter damping is much higher. It means we can probe much smaller scale. Of course, there's also a limitation. If you go to too smaller scale, then neutral hydrogen has similar velocity as well. So this 20 centimeter spectral line gets Doppler broadened. So there's still upper bounds. And there's a damping of 20 centimeter signal cell, but I'm just showing this picture to give you an impression that we have a huge Fourier model available from 20 centimeter data. And on top of that, for the comparison with CMB, CMB just gives a one snapshot at redshift of 1100. But for 20 centimeter, we can get a 3D picture because we know this emitted or absorption emission is 20 centimeter in rest frame. So by measuring the Doppler shift wavelength, we can get a tomographic view, redshift dependence as well. So we have a much finer resolution than CMB map. And on top of that, we have a three-dimensional tomographic view of the universe. So this is great. Right? So I'm going to talk about how this 20 centimeter can put some bounds on some cosmological model of particle physics model. And the way it works, the way 20 centimeter can work is following. So we have some flashlight in the background. Let's use CMB as a flashlight. So we shine the CMB photons onto the gas of neutral hydrogen. So some of CMB photon can go through this neutral hydrogen clouds, represented by temperature, spin temperature, and optical depth tau. And also there's the emission from this neutral hydrogen clouds itself as well. But those guys also go through the finite optical depth. So what we're going to get eventually is so-called brightness temperature, which is the intensity of the photon flux after the CMB photon goes through the neutral hydrogen clouds. So what we measure is a so-called differential brightness temperature, means TB minus TCMB, because we always measure this brightness temperature with respect to the background temperature. And here I use the CMB as a background. So the difference between brightness temperature and the background temperature is what we're going to measure, so-called the brightness temperature. And we can expect what would be the cause of the fluctuation of this differential brightness temperature. So one cause is due to the baryon fluctuation, baryon density fluctuation. This delta represents the fluctuation of the neutral hydrogen distribution. So some parts of the sky have denser density than another part. So 1 plus delta times omega b represents the how inhomogeneous this neutral hydrogen distribution would be. And also this fluctuation of differential brightness temperature is also caused by the inhomogeneity in an ionization fraction. Some parts of the sky is 50% ionized, while another part of the sky is 10% ionized. So neutral hydrogen fraction is different depending on which part of the sky you are looking at. So those are two main reasons why we expect some fluctuation in the brightness temperature. And pictorially, what you see is that we measure the CMB background, but if you take a close look at it, there's some small deviation from the Parkes black body. So some parts, its emission above this residual zero horizontal line, and some parts it's a little bit below. Below means there's absorption from this gas. And this spin temperature is hotter than background CMB. It's above this residual zero line. So by looking at how deviated this brightness temperature would be with respect to the flashlight of background CMB photon spectrum, we can measure the nature of this neutral hydrogen. Okay, so this is the way we make a 20 centimeter measurement. And let me talk first about how this mini halo would affect this 20 centimeter signal. So we use a CMB photon as a background. A CMB photon goes through this diffuse neutral hydrogen atom, neutral hydrogen, this represented by these red dots. But in our scenario, there are lots of mini halos as well. So those CMB photons also go through mini halos as well. And the mini halos has a very dense neutral hydrogen inside it. And it turned out there's a lot of emission from this hyperfine splitting of the neutral hydrogen if they go through mini halos. So compared with no mini halo scenarios, if there's a lot of dense neutral hydrogen clouds, we expect more emissions. So signal of 20 centimeter would be enhanced. This differential brightness temperature would be enhanced because there's a lot of localization of the dense neutral hydrogen class, thanks to the existence of the mini halos. So we naively expect this delta TB would be proportional to abundance of the mini halos. So this figure here shows this enhancement of 20 centimeter signal or enhancement of differential brightness temperature thanks to the enhancement of the mini halo abundance would be like factor 5 or so. So this dot black curve is no action scenarios. This black solid is with action, so enhancement of mini halos. So if there's more mini halos, more neutral hydrogens, so brightness temperature would be enhanced thanks to lots of dense neutral hydrogen, abundant mini halos. And on top of that, we naively expect this 20 centimeter signal to be proportional to underlying dark matter distribution. This is natural because the neutral hydrogen distribution presumably follow the underlying dark matter distribution as well. So the shape of this power spectrum of difference brightness temperature, and this is black curve here, is pretty much same as the dark matter power spectrum because distribution neutral hydrogen would be more abundant when underlying dark matter density is higher. And this ratio between matter distribution, matter fluctuation, CL matter, and the fluctuation of 20 centimeter neutral hydrogen fluctuation is related by so-called bias parameter. So bias parameter is just a ratio between matter per spectrum and 20 centimeter per spectrum called B. And the ratio actually decreases in action scenario compared with no action scenario. So this red one is the bias for the no action scenario. The dashed one is for no action scenario. And the red one is the bias parameter for the action scenario. And this is also reasonable because in a no action scenario, the abundance of mini halos is smaller. So it means the distribution of the mini halos would be more biased toward the denser region, denser dark matter density regions. So as a result, the bias parameter is bigger for no action scenario. For action scenario, there are more abundant halos, so it's less biased towards the higher density underlying dark matter density region. But this decrease of the bias completely gets dominated, overwhelmed by this number density enhancement of the mini halo abundance. So as a result, we expect action scenario to give a bigger 20 centimeter signal, thanks to huge enhancement of the small scale structure. Is it okay so far? So this is a comparison. This black one is action scenario with lots of mini halos, and this dotted black one, for instance, is a no action scenario. So we get a factor 10 enhancement in the fluctuation power spectrum. Okay, so it is good that we have a more abundant mini halos, meaning more neutral hydrogens. So we just can calculate the sensitivity on this ice curvature perturbation, or namely sensitivity, this K oscillation cutoff, which represents the ice curvature power amplitude, also cutoff scale. And we just did a Fisher matrix analysis, likelihood analysis. And as I said, if K oscillation gets too big, amplitude is inversely proportional to 1 over K2 cubic power. So amplitude gets smaller. So the difference between no action scenario and action scenario gets smaller and smaller. So we cannot probe too big a case K, because the 1 over K2 cubic power becomes too small. Amplitude of the ice curvature perturbation becomes too small. So there's some upper bound of K. And there's also a lower bound of K, as I mentioned. If amplitude of Voice curvature perturbation gets too big, small scale structure got formed too early, so they get merged into a bigger halo. So in a 20 centimeter sensitive region, mini halo range, there may not remain so many small halos anymore. So there are some particular range of K this 20 centimeter signal is sensitive to. So from this figure, for instance, we can see this upper bound of K is like 10 to 5 or so. So this black one is 10 to 5 when the error bar sigma K over K being was 100%. So it means as long as K is below this value, we can prove the action parameter. So for instance, if action is a temperature independent in equal 0 case, then this crossing of the purple line at K to the 5th is the upper bound of K, which 20 centimeter signal can be sensitive to. It's about 10 to minus 13 eV or so. So that's why this bound of 10 to minus 13 eV came from. So the reason why we get such a like 4 order of magnitude or even like 7 order of magnitude better than CMB or Lima alpha is because we can prove very, very small scale from the 20 centimeter. Is it clear? And this 20 centimeter, as I mentioned, still it's a future prospect. So it's a little bit unfair to compare Lima alpha bound and CMB bound because they are using the actual data. So this is future data. So this is just a prospect to give you some insights how good 20 centimeter signal can be. And the reason why 20 centimeter signal is hard to deal with is the foreground. So there are lots of emission which becomes obstacles to the 20 centimeter, this radio signal from 20 centimeter neutral hydrogen. So the signal in terms of temperature is of order 10 millikelvin or millikelvin, but the foreground is much, much bigger, even order 5 Kelvin or 0.8 Kelvin. So we always have to deal with, find the, optimize the signal to noise. We somehow have to remove the foreground. And one of the reasons why it gets harder and harder is because of the synchrotron radiation. So this is 20 centimeter signal and CMB signal. 20 centimeter signal is bigger than CMB signal because for the fluctuation, CMB is just 10 to minus 5, right? Delta T over T is 10 to minus 5. 20 centimeter signal, delta T over T is like 0.1 or 0.01. But the frequency is different between CMB and 20 centimeter. So CMB frequency goes like over the 10 gigahertz or 100 gigahertz. But 20 centimeter is a radio wave, so we have to go to 1 gigahertz. So at 1 gigahertz, the synchrotron radiation keeps increasing, so completely dominated by synchrotron radiation. So the name of the game here for the future 20 centimeter would be this tackling the foregrounds. So now I'd like to briefly talk about why don't we use foreground-free measurements using radio source instead of a CMB background. So basically, this is a foreground-free measurement. So it's, in a sense, very clean. So the basic mechanism is simple. Instead of CMB flashlight, let's just use a very, very bright source like quasar, which emits huge radio flux. And if there's a dense cloud like mini halo, which has a very dense neutral hydrogen, then this flux gets absorbed by the big optical depths in these mini halos. So if there are more mini halos, means more absorption lines. So we can basically count how many absorption lines we will have. So compared with no action scenarios, we should expect lots of absorption lines if we just keep looking at the one particular part of the sky where this bright quasar exists, for instance. So it actually looks like a forest. So there's a uniform decrease from the diffuse neutral hydrogen. So there's neutral hydrogen, even if there's no mini-halo, there's a diffuse neutral hydrogen everywhere. So there's a uniform absorption by the diffuse background, but on top of that, there's a very sharp absorption line corresponding to the absorption by the dense mini-halos. So we call it 21 centimeter forest, like lime alpha forest. So this is background free because the source is very, very bright. So if in an experiment, if you look at one particular pixel, it's basically very, very shiny, very bright spot. We just count the number of absorption lines. And coming back to this ice curvature perturbation per spectrum, if there's a ice curvature enhancement correspond to mini-halo range, we expect number of absorption line increase. So this middle plot represents the tau is optical depth. So the area below these lines are number of the absorption lines. And if K oscillation is too big, then because ice curvature perturbation is proportional to 1 over K2 cubic power, the difference between this black no action scenario and the action scenario gets a little bit too small to see. But if K oscillation is a little bit bigger value, means ice curvature perturbation gets a little bit bigger, so the difference between black curve and the other colored line gets a little bit bigger. But as I said, if K oscillation gets too small, if ice curvature perturbation gets too big, then small halos got formed too early. So if we look at the redshift 10, most of the structure may already have merged into black and dark haze and big halo, which 20 centimeter cannot prove. So there's the upper bound and lower bound of K, as I mentioned. So this shaded region corresponds to that particular K scale, which 20 centimeter forest is sensitive to. So again, there's a one-to-one correspondence between K oscillation and action mass. So from this 21 centimeter forest study, we got comparable bounds, 10 to minus 12 eV. Using CMB background, we got 10 to minus 13 eV, but one order of magnitude doesn't bother me because we did some simplification for the noise treatment in a CMB background paper. I just assumed that all the noise comes from synchrotron and I ignored the systematics. So I was happy to get the consistent naive results that both 20 centimeter forest and the CMB background 20 centimeter signal gives the comparable results. It's reasonable because both are using mini halos. One tricky thing though is that 21 centimeter forest, because we are using very, very bright source in a high redshift, foreground can be 0, but the signal may be 0 too, because we may not have such a bright radio source at such a high redshift. High redshift means redshift above 6 when universe is still partially neutral, so that there are lots of neutral hydrogen on the way from the point of emission toward us. And for the SK-like experiments, we need a sensitivity limit of like 10 millijansky or so. So the question is, if we have such a bright radio sources at redshift 6 or so, which emits lots of radio photons of order 10 millijansky or so. We still haven't found yet, but there are a couple of promising radio loud sources. So this is one example. This red one represents a radio loud source. So radio loudness often are parameterized by the ratio between the visible range photon emitted from that source and the radio frequency photon emitted from that source. Source frequency range can cover like visible to radio. It does not emit one frequency. There's a broad range of the frequency. But if this emitted photon from the radio sources is dominated by the radio frequency, we call it radio loud. So this dark one, gray one is a radio quiet, but above those gray region is called radio loud. If we extrapolate the quasar at a low redshift to high redshift, we naively expect 10% of the whole quasars would be radio loud. And the question is, if we have a very, very bright source at a very high redshift, and this plot is from the actual measurement, so we've already found this P352 represented by red one, which is shining with the flux of order 10 to 100 millijansky at a redshift of 6. So it was first observed by optical telescope, and the radio telescopes are now doing a follow-up survey to make sure that it's really radio bright sources, and also we have to make sure that this bright radio source is surrounded by dense environment so that we can expect lots of absorption from dense neutral hydrogen clouds around radio bright source. So this is promising. So in the future, we may actually find that 20 centimeter forest from the actual data. Okay, so let me wrap it up. So I talked about the post-inflation peak breaking scenario where we can expect enhancement of the small scale structure formation. And one application of that was to bound the action scenarios. And we got a very impressive number compared with current bounds from 20 centimeter. Okay, thank you.
Thank you, Kenji.
Yeah.
Are there any questions or comments?
I have a question, Kenji.
Yeah.
We don't need. Do you think that you can find your mini halos by other kind of searches? I'm thinking maybe X-ray searches or via the searches of substructures in our galaxy.
So as long as we have an angular resolution, it's possible. So the question here is if you can go to such a high K. Right, so the reason why CMB and Lime alpha cannot probe such a mini halo I'm talking about is because they don't have such a high angular resolution. So you're asking if mini halos can emit some other frequency, not radio frequency, but other frequency photons, and if you can measure it or not is your question.
Yeah, that would be yeah, whether for instance they emit X-rays.
Right. So it doesn't have to be neutral hydrogen. If there's some lot of matter density in the mini halos, and then if it emits some particular frequency, yeah, it may be possible. But because we are probing the size of the mini halos, your experiment has to have a very small angular resolution. So I don't know if we can probe such a small scale without like a radio telescope interferometer. One of the reasons why 20 centimeter SK can probe such a small scale is because we can use an interferometer so that the radio telescope is farther away, so that we can probe the very, very small scale.
Sure. And the other part of the question was whether these can show up in substructure search. I'm thinking of experiments like Gaia, for instance.
So probably if those small scale structure can be enhanced, you may, I think, Gaia. So yeah, because there's a lot of small scale structure enhancements, right? Because there's a ice curvature propagation at a very small scale. So if the Gaia is good at the measurement of like stars, study of stars, right?
Yes,
So,
it's
yeah,
the
right.
study of the small scale potential of
Right.
galaxies.
So one possibility could be if there's lots of substructure inside the galaxy, for instance, and if those small substructure can affect the gravitational potential well, for instance, then you may be able to see some effects, I think.
Okay, thank you.
Yeah, because the distribution follows underlying dark matter distribution. So if there's a small substructure affecting those underlying dark matter distribution, I think, yeah, by looking at the motion of the stars may be possible.
Mm-hmm. Thank you.
Yeah.
Are there any questions? Other
So-
questions or
So
comments?
in the end, this consideration should give an upper bound for axion dark matter abundance for a given axion mass. Right.
Upper bound on the abundance.
Yeah.
Yes, upper bound on the abundance. So here
If
I
axion
assume
dark matter is much, then the mini halos will be supposed to be
suppressed. Yeah, suppressed. So this ice curvature perturbation amplitude is proportional to the action abundance squared. So omega A action divided by omega matter. So if 10% of the whole dark matter is action, the ice curvature amplitude is suppressed by 10% square, so 0.01. Is this what you're asking?
No, I mean, so this consideration eventually gives an upper bound for axion dark matter abundance for a given
Abundance too. Yeah. So, right.
You
So
just to show that this scenario can constrain axion mass larger than 10 to the minus 13 electron volt.
Right. So that bounds is assuming 100% dark matter action.
You mean then just it's excluded?
Yeah. Right. Yeah.
But precisely,
it's not excluded, right? Still, it's possible, right? If it's such a small mass range, 10 to the minus 13 eV with 100% action dark matter, because there's no observation to probe such a mass range, right?
so if axion mass is 10 to the minus 10 electron volt,
Yeah.
then what does this scenario imply? What
So-
does consideration imply?
So 10 to minus 10 eV, we cannot probe it because it's too small a scale, even for 20 centimeter or mini halo.
You mean this mass range is allowed?
Yeah, it's allowed. So action mass has to be bigger than 10 to minus 13 eV. So 10 to minus 12 or 10 to minus 10. So if the action mass is 10 to minus 14 eV or 10 to minus 15 eV, we can probe it.
If axion mass is 10 to the minus 14 electron volt,
Yeah, it's
then,
lighter, so we can see it by 20 centimeters, so we can exclude it.
so if that axion comprise the whole amount of dark matter, then
Yeah,
it's
so,
excluded. But if
Right.
it's 10% less than the
Then it gets weaker.
yeah, but I think you don't show the exclusion plot for in terms of axion mass and the axion dark matter abundance.
Yeah. So in my paper, actually, I also considered the difference, like 10% action dark matter, for instance. Then the bound gets weaker. Because
but not the continuous function of omega A.
Right. So I just, so right. But you can sort of naively extrapolate by just taking some points because it will be probably continuous bounds. So you can put a bound on x-axis MA and the y-axis omega A.
Yeah.
Action abundance, and probably you can
Right.
draw
Yeah.
the
We
counter
can
plot.
straightforwardly do it, but I just want to check.
Yeah. So,
how much strong the bound is.
Right. Yeah, and the dependence on action fraction is quite big because ice curvature perturbation is proportional to abundance squared. So if you use, instead of 100%, if you use 10% action dark matter, the ice curvature perturbation is 1/100. So ice curvature perturbation gets suppressed quite a lot.
Yeah.
Right. And so this bound is assuming a whole 100% dark matter. But as you said, if you assume it's partial dark matter, this bound gets weaker and weaker.
Yeah.
Yeah. Right.
Okay. Yeah.
Yeah.
Any other questions? I have a question. You consider the scenario that PQ symmetry is broken after inflation. So are there any assumptions about the string formation?
So
or its stability? Are there any effects from string, cosmic string?
Yeah, there should be. So for instance, because there are topological defects here, the action would be produced from the decay of the string as well.
Yes.
So here I assumed whole dark matter coming from this misalignment mechanism.
Mm-hmm.
But some parts of the action actually come from the decay of the string as well. So that changes the bound on the mass as well. Because this mass bound coming from 100% dark matter coming from the misalignment mechanism. So that's one thing, effect of the string. And another thing we discussed briefly mentioned in the paper is that it has to be post-inflation PQ symmetry breaking scenario. Because if PQ symmetry breaking occurs before inflation, there's no such a big ice curvature perturbation because horizon patch gets stretched out. So whole inside the horizon is just one theta value.
Yeah.
So we have to justify this post-inflation breaking occurred after inflation, or even if symmetry breaking occurred before inflation, it got restored after inflation and then rolled down to the Mexican Hunt potential. So this, if we assume, if you stick to post-inflation scenario, then as you said, there's the effects of the decay of the string or effects of action string, topological defects. And also there's some bound on the action decay constant as well, because decay constant determines when it gets broken. Yeah.
Thank you.
Yeah.
So are there any other questions? I don't see others. So let's thank Kenji again. And we have 10-minute break. So shall we resume at So let's start the second talk of today's workshop. So the second talk is about gravitational waves and axion-like particles. It will be presented by Dr. Benjamin Stefanink. So please.
Okay. Can everyone hear me?
Yes.
Okay. So yeah, I'd like to talk about, I'm currently at the University of Zurich, but I want to talk about some work I did at my previous institution, which was Mainz in Germany, working with these fantastic collaborators here. And yeah, let me just go ahead and get started. So I want to start off with a brief sketch, just what we actually know about cosmological history. At very early times, we have lots of evidence now that there was some period of inflation at a very high energy scale, which is bounded to be at most the gut scale. And then we know at lower temperatures or lower energy, there should be around temperatures of 10 to minus 3 GeV or so. We need to have a thermoplasma in order to have successful Big Bang nucleosynthesis. And then we think we know more or less what happens from that point until the present time. But in between this gap in energy from BBN until inflation, which is in principle up to 19 orders of magnitude, we don't know what happens. We think there are many things we think should happen, such as some mechanism for reheating the universe after inflation, baryogenesis should happen somewhere in there, electric phase transition, so on and so forth. But one other thing we can think of is axions or axion-like particles leaving some kind of signature in this era through their dynamics. Of course, if we want to probe behind the surface of last scattering, we need a messenger which can carry information from this point in the universe. So a natural thing to think about is, can we use gravitational waves to do the job? So I want to focus mainly on what I call dark axions and their dynamics in the early universe. So if they have a mass which is heavier than the Hubble rate at BBN, then these axions will become freely oscillating in the early universe at some point. So the mass scales we're talking about here would be greater than 10 to minus 16 eV. And by dark axions, I mean it's possible these dark axions couple to some hidden gauge group rather than the standard model, or if I allow standard model couplings, they only couple very weakly. So in this language, the axion becomes invisible. I can't find it with looking for its coupling to photons, for example. And I really want to just try to probe it via its gravitational effects. So here you would usually think about things like superradiance, but this is mainly a probe for very light axions, and I want to focus on heavier mass range. So yeah, that's the model that I'll think about here is just a simple toy model. I have some axion-like particle phi. It's coupled to a dark photon, some Chern-Simons term. This dark photon is some hidden U1x. And just as a point for people who might already know a little bit about this process, I can produce this dark photon non-perturbatively when the ALP has non-trivial dynamics, so when it's rolling in some way. And mathematically, this is the same process as what you'd get from preheating axion inflation. The difference here is that those processes are sort of tied to the mass scale of inflation, whereas we're going to consider processes that happen after the inflation scale. So here's just it's a toy effective field theory consisting of this axion and this dark photon, which we at this point take to be massless. So it's just the theory of the axion and the dark photon and this Chern-Simons term, where you have this coupling constant alpha here, which is not exactly the fundamental coupling constant of the U1x. Instead, it's some effective coupling constant, which includes anomaly coefficients. This F is the scale of spontaneous symmetry breaking for the axion-like particle. And yeah, and here you'll probably catch me using the word axion and axion-like particle interchangeably. So whenever I say axion, I just mean axion-like particle in general. And we assume that there's some explicit symmetry breaking of the global symmetry at the scale lambda, which gives rise to a potential and a mass for the axion-like particle. Here we take it to be roughly cosine in form, but it won't really matter as long as it's sort of locally quadratic. Okay, and just by sort of vacuum misalignment arguments, I have some constraint on my initial conditions. This is just because when the potential is generated, I don't expect that the axion there's no reason for the axion to be at the new minimum. So generically, you expect it to be some order 1 times f in field space away from the minimum when it appears. And if the potential is generated at a time when the axion is still damped by Hubble friction, it will just stay pinned in its whatever position it's in until the Hubble becomes of order its mass and then proceed to roll down to the minimum. So this is the kind of initial conditions I'll be thinking about. And so in principle, I have this model which has 5 parameters like this alpha, f, axion mass, and I have 2 initial conditions. But if I apply misalignment arguments, then I can just reduce this to a 3-parameter problem where I have axion mass, the axion decay constant, and this effective coupling. Okay, just to give some sketch of the cosmological history I'm thinking about here, I'm imagining here that the global symmetry is the PQ symmetry, if you will, is spontaneously broken before inflation. So then I have an inflation, and I zoom in on one patch where the theta is uniform, the misalignment angle is uniform. And somewhere between the end of inflation and Big Bang nucleosynthesis at some scale, square root of the axion mass times 1 Planck, this axion will start to oscillate and transfer its energy into dark photons. And in a process which I'll describe more in detail in just a second, you'll also get gravitational waves. So the way this works is when the Hubble rate becomes of order the axion mass at a temperature given by this, then the axion can start to roll down to the minimum. So at this point, at the time of when oscillations begin, I have roughly the energy density just of a harmonic oscillator, where this phi initial is given by misalignment. So just order 1 times f. And then I can ask the question, what's the density fraction of the axion at the time it starts to roll? So I just divide the axion energy by the total energy density of the universe, which is 3m Planck squared h squared. And because at the time I start to roll, Hubble is over the mass just cancels here. And I get something which scales like theta f on m Planck quantity squared. So this will be an important quantity for me because in the end, this thing is what controls the energy budget of my axion, and I'm going to use the axion as my gravitational wave source. So this is something I want to keep track of. And I'm gonna, because I don't want the axion to dominate the energy density of the universe, because then I would have a slow rolling field dominating the energy density of the universe and have some inflationary type behavior. I want the axion to be subdominant to, say, some standard model radiation bath, which is dominating the energy density. But if I want to source gravitational waves with a large amplitude, I shouldn't take it too small. Otherwise, I kill my gravitational wave signal. So I need f below m Planck, but not so far below, like say 1 order of magnitude or so. So 10 to 17 GeV is what we'll be thinking of. And just as a simplicity in my initial conditions, I take that there's no initial abundance of the dark photon. So it'll only be sourced by the axion, but this is not a necessary condition, just a simplifying one. Okay, so the dynamics look like this. I have some radiation dominated universe, and the axion satisfies something which looks like the usual Klein-Gordon equation on the left-hand side. But now, because of the Chern-Simons coupling, I have this source term. And these E and B's here are not the photon ones. They're the dark photon electromagnetic fields. And the dark photon itself obeys what again looks like a normal wave equation on the left-hand side with a new source term as well. And here you see, very importantly, the source term is proportional to the conformal time derivative of this prime is derivative with respect to conformal time of the axion field. So unless the axion's rolling, I don't have any source term here. And because I started with initial conditions where my axion field has like, say 10% of the total energy density and the dark photon has no initial abundance, it should be clear just by energy arguments that the energy will flow from the axion field into the dark photon. So this term will act as like say friction on the axion field and deplete the amplitude while the dark photon amplitude grows when the axion is rolling. But of course, this is at the classical level, and in the end, I want to study production of these dark photon quanta. So I just canonically quantize my dark photon field here, and it's convenient to work in the helicity basis. So these V lambdas are the mode functions of a massless U1 gauge boson. So I have two helicities left and right, which are labeled by this lambda. And it's nice to work in this basis because it's sort of, I take this expansion for the dark photon, I plug it back into this equation of motion, and it sort of trivializes the cross product. So I get, in the end, I get an equation of motion for these dark photon mode functions, which looks like this. So these V lambdas satisfy this, where plus and minus indicates the helicity. And you see I have now what looks like a simple harmonic oscillator with a time-dependent frequency, except I have a dispersion relation, which depends on the, again, on the axion velocity. So you see that when the ALP is rolling, there will be some range of momenta, whether for the plus or minus helicity, where you have tachyons, where omega squared is negative. So those modes will, instead of obeying simple harmonic oscillation, they'll grow exponentially according to the magnitude of omega. Okay, and because somehow this system has to break parity when the minimum of the potential appears, I either roll down from one direction or the other. So one helicity will go tachyonic first. I don't know which one, but one of them will. And because of the exponential nature of the growth, the first helicity to become tachyonic always gains an advantage over the other one because I have the biggest amplitude initially, and then due to friction from Hubble and also from particle production, by the time I oscillate to their side of the potential and the velocity change of sign, I'll have lost some amplitude. So when the other helicity goes tachyonic, it won't have as efficient of growth. And you see that here I'm showing the dark photon power spectrum. And this red color is whatever helicity goes tachyonic first, say left. And you see it just really, it's a very, very good approximation to say you only produce one helicity. The other one is exponentially suppressed relatively. So you can just go a bit further and say, what are the actual modes that are tachyonic? You just look at the range of modes for which omega squared is negative. It's these ones. And then just to get a rough idea of how it scales, the overall scale in the potential was like theta squared m squared f squared. So square root of that is what I like is a typical value for my the biggest value my velocity can be. So if I put theta m times f, I find that the modes which are normalized to the mass, the modes which are less than alpha theta are the ones that are tachyonic. So here you see in this plot, like I have growth of modes which are in terms of k on m less than 50. So here you already see what I'm thinking of for alpha, the product alpha times theta should be order 50, which means I need for theta order 1, I need large coupling. Okay, something like 50. And I can also look in see what there's a k which minimizes omega squared. This is the most tachyonic mode, if you will, the one that grows the fastest. And this is half of this value, so alpha theta m on 2. And I can sort of understand this plateau-like behavior of the gauge boson power spectrum as this scale, most tachyonic scale, where most of the energy is being deposited, which is a monotonically decreasing function because this phi prime only decreases. So I have some k tilde at the start of the process, which then moves to lower values and traces out this plateau-like region. So that's roughly what's going on in the power spectrum here for the dark photon. So let me get to gravitational waves. So you have these exponentially growing modes, dark photon modes, and these guys, they're not zero, they have quantum fluctuations. So they have a non-vanishing variance, which is, and then these guys are growing exponentially. So the underlying quantum fluctuations are anisotropic. So as the modes grow, eventually they become amplified into this underlying quantum fluctuations become amplified into some classical rapidly time varying source for gravitational waves. So they source this anisotropic stress tensor, where this thing in terms of the dark photon electromagnetic fields looks like this. So it's almost like E squared plus B squared, what you think about for energy of electromagnetic field, but it's the tensorial combinations. And these guys, the E's and B's, contain these exponentially growing dark photon mode functions. So in the end, because of the underlying fluctuations of the dark photon, you generate anisotropic stress, which also has a non-vanishing variance. And this is our gravitational wave source. Okay, so here's some results from our numerical simulation where it's a linear analysis where there's not yet it's just axions going into dark photons. There's not backscattering from the dark photons into the axion field, which also we have an initial condition motivated by the period of inflation where the axion field is initially homogeneous and you produce dark photons with anisotropies. In principle, there's also a backscattering process where dark photons backscatter into axions and induce inhomogeneities, which I'll talk about a bit later. But at least in the results of the linear analysis, you have this plot for the energy density of, here's the red is the axion energy density, the blue is the dark photon, and they're normalized to it's a co-moving energy density for a given species. So when the red line here is horizontal, it's scaling like matter, and when this one is horizontal, it's scaling like radiation. So you see in the beginning, when the Hubble is greater than the mass, this thing is actually still overdamped, and it actually behaves a little bit like a CC, so the energy density grows a bit. And then you become freely oscillating. This thing is, you see it oscillating here, so it's scaling like matter. And during this oscillation process, you're pumping the dark photon modes. And then when the modes, dark photon modes have energy of order the axion, you start to see a back reaction where the axion starts losing a large fraction of its energy at the same time the dark photons peak. So this is the, and then it looks like you have some dynamics here where you can really suppress many orders of magnitude in the axion abundance. And finally, this process stabilizes. It stabilizes at some non-zero value of the axion amplitude. So this remaining piece could in principle be cold dark matter. This process was first pointed out by these authors, where they used it to, in the case of the QCD axion, to deplete some of the QCD axion abundance when you had a large decay constant. So you could use it as a way to go above the traditional bound of 10 to the 12 GeV for the QCD axion when you don't tune the misalignment angle. In our case, we also looked at the gravitational waves as this process is happening. So here you see, it's kind of hard to see, but the line styling, the vertical line styling here matches the corresponding line styling on the gravitational wave spectrum here. So during this initial drop, you produce the blue part of the spectrum here. And by the time you get to this like scale factor of order 10, in terms of the initial scale factor, you've produced most of your spectrum already. So the gravitational wave spectrum is mainly produced in this initial phase here. Okay, and these are some benchmark points we used for this plot. And like I said, we'll always be considering F around 10 to the 17 GeV and big coupling. Okay, so I'm just going to talk a little bit about the different phases. The first phase is this tachyonic instability phase. This is actually the one that's most important for gravitational waves. I said before that you need omega squared to be negative to have tachyonic growth, but actually the real condition is a bit more subtle, because I need the mode to be, the frequency to be negative enough so that the mode grows efficiently within one conformal oscillation time. So that leads to a bit more stringent condition, and you end up having this what we call the tachyonic band, where you have this central value k tilde, the most tachyonic mode, and you have some band around that which is tachyonic, and you see as the scale factor grows, the band closes. So you can actually estimate, just assuming that the amplitude of this thing damps down like matter, which is just a rough approximation, you can estimate when this band should close. And you find it closes around when scale factor has increased by a factor of 10 or so. So this is the region here we call the tachyonic region. And this is the one, like I showed you on the previous slide, that dominates the gravitational wave spectrum. So we can use this as a rough time. If we want to estimate the gravitational wave spectrum as being emitted instantaneously, we can use this as a rough estimate of what that time should be, where when the scale factor is grown by a factor of 10 and this most tachyonic scale is order 10 times the axion mass. There's another phase, which is the one responsible for depleting most of the axion relic abundance in the linear analysis, at least. And this is what we call the parametric resonance phase, because I can study it by writing my mode equation, the equation for my mode functions in terms of a Matthew equation, which is well known in the engineering field. So they've studied these the instability bands of this equation, and when the amplitude is large, you get you have these broad resonance bands, but after the tachyonic phase, you already deplete most of the initial amplitude by a lot. So when you have small amplitude oscillations, then the Matthew equation, you're really dominated by these so-called narrow resonance bands of the Matthew equation. And for small amplitude, you're really dominated by the n=1 narrow resonance band. So what I've done here is I've shown on the right, in terms of the dark photon power spectrum, the location of these vertical lines are the location of this narrow resonance band as a function of time in terms of the scale factor. So again, here, vertical line styling on this plot matches vertical line styling on this plot. So I see that after the tachyonic phase has ended and I begin this parametric resonance phase, it's this dashed line, which corresponds here to the narrow resonance band entering the most highly pumped part of the dark photon power spectrum. And then, so there I get very efficient depletion of the axion relic abundance because the coherent axion condensate is resonating with dark photon modes that are highly pumped. And this process continues until I get to the solid line, where I see that I'm falling off the end of the highly pumped part of the dark photon power spectrum. So in this way, I can understand why the process shuts off is because I've just fallen off of the narrow resonance band. In the conformal language has moved out of the range of the dark photon, the highly pumped part of the dark photon power spectrum. In the real-time language, it would be the power spectrum redshifts through the mass, essentially, which controls the oscillation time. And I can even get an analytic estimate on, what's the final value of the scale factor where this process shuts off. But I know an estimate for this shoulder of the power spectrum because it's the most tachyonic scale, this k tilde, at the beginning of the process. So I can just use that to derive a expression for the final value of the scale factor, and it just is controlled by alpha times theta, which in this plot here was 66 or so, and you see it matches quite well with where the process shuts off. So this we think we understand. Okay, back to gravitational waves. Just to do some naive dimensional analysis, so I get an idea of what I should expect before I do my numerical simulation. I know that I have this, the axion is acting like the source for my gravitational wave, so my energy in gravitational wave should be limited by that, which is again this F1 Planck squared scaling. And there's a sort of a naive dimensional analysis estimation for cosmological gravitational wave signals, where you have some characteristic scale where most of the energy is being deposited. For us, it's this k tilde at the time of emission. And the amplitude is roughly set by two pieces. There's a piece which is the source density squared, because this is the gravitational wave 2-point function. And then there's this piece in parentheses here, which is, it's really comparing this mode where I put most of the energy into the size of the horizon at the time of emission. So it's telling me that to get a big signal, I need to put the energy in a mode which is of order the size of the horizon. If I put the energy in a very sub-horizon mode, I pay a penalty. And in the end, this is a factor which is like, for a gravitational process, I always have to compensate a 1/m Planck squared somehow. So this is this factor in terms of cosmological language. So if I just estimate these guys in our model, I find that the peak frequency is roughly set by the axion mass with some factor alpha theta here. And because I pay the source density squared, I have now F1 Planck to the 4th, which is, this is what controls the amplitude of my gravitational wave signal. So I really cannot go very far away from Planck if I want observable signals. Okay, so now we see this is a gravitational wave spectrum computed from our numerical simulation. And we see that the scaling relation does this naive dimensional analysis estimate actually does quite well in terms of predicting the peak location. And yeah, this gravitational wave spectrum is peaked, and you see that here I've decomposed the total signal, which is the black, into the underlying gravitational wave helicities. So the red curve is like say left polarized gravitational wave, and blue is the right. And the reason why I get a polarized spectrum, so the peak is dominated by the red polarization, is because I've somehow inherited the parity violation that I had in the dark photon population. Because remember, to a very good approximation, I only produce one helicity of dark photon. So I can think of saying, okay, I have this population of dark photons, which is, I only have one type of helicity. So I can take two dark photons and I can add them of the same helicity, of course, and add them in, say, anti-parallel. so then I end up with a low momentum gravitational wave, which is unpolarized because I have to flip the velocity of this guy. The other thing I can do is take two dark photons, which are again similarly polarized, or same polarization, and add them in parallel, and then I get a high momentum gravitational wave of momentum, yeah, like roughly 2K, and it's completely left polarized. So those two processes, like the high momentum piece giving the peak and being completely polarized, is what's going on in the peak region here, and the tail is the low momentum guys, which are roughly unpolarized. Okay, so yeah, the peak being completely chiral is it's a smoking gun signature for this type of model. Okay,
Wait,
and
I may miss.
yeah.
Why the amplitude of gravitational wave is inversely proportional to alpha in the previous page?
This is coming because alpha enters this this peak scale. So in the end, you pay a little bit of a penalty if you crank alpha too large, because you're making the scale where you put the most energy more sub-horizon. You see what I mean?
Mm-hmm.
Here, alpha enters, yeah. You're pushing the peak scale to higher momentum, so more sub-horizon.
I see.
Yeah. Okay, so here's just like a sketch of what you can get if you consider ALPS of various masses. So in the end, it's as I said before, the frequency is mainly set by the axion mass. I need to redshift to the present time, so I put in some factor of temperature today divided by temperature at the time of emission. And this temperature at the time of emission is roughly square root of m times m Planck. So in the end, I pick up a scaling which goes like the square root of the mass, but the story is still the same. By changing the axion mass, I change the location and frequency space of the gravitational wave peak. And the amplitude is mainly set by this f1 m Planck to the fourth. And then as just a crude approximation, I say, okay, I emitted my gravitational wave signal in radiation dominated period. So the redshifting should go, it shouldn't redshift during the radiation dominated era. It should only pay the redshifting during the matter dominated era. So I can just roughly say, okay, I just put the same scaling as the ordinary photon bath, and that's gives me the right order of magnitude. So just to give you an idea of what kind of masses we're talking about, to be in the range of pulsar timing arrays, I need masses which are in the 10 to minus 13 to 10 to minus 10 EV region. And here I'm always talking about big F, theta order 1 and alpha order 50 to 70. We check an effective and relic abundance. Here, at least in the linear analysis, the relic abundance is quite sensitive to the initial conditions. Like if I change theta by a little bit, I can change the relic abundance by an order of magnitude or so. So we consider a factor of 2 here to be roughly okay. And in the to get into higher frequency range, I need, like for LISA range, I need 10 to minus 2 to 1 EV for the axion mass. And finally, for even higher frequency detectors like Einstein telescope or BBO Desigo, I need 10 to 2, 10 to the 6 EV. Okay, in the end, we decided that instead of running the simulation every time to get these spectra, we just want to have some fit template where we can go from our underlying fundamental parameters, which were alpha, m, and f, to the gravitational wave spectrum without needing to do a simulation. So we just fit an ansatz where you have, at low frequencies, you have some power law. At high frequencies, you have some exponential fall off, and then there's the transition region, which gives the peak. And we know the scaling relation we had works pretty well. So we just normalized. So this f tilde here and omega tilde are the amplitude and the frequency normalized to what you'd expect from the scaling relations. And then we just put in some factors, alpha s and fs, which correct by the order 1 factors that the scaling relation was off. And then the gamma controls the exponential fall off, and the p is the power law for low frequencies. So with this, we can make a nice plot like this, where each experiment gives you a signal to noise ratio that they consider to be detectable. And you can just, using this template, you can calculate various SNRs and find where the boundary is. So that's how we generate these curves. And the really interesting feature about these models is that because larger decay constants mean that you have a bigger gravitational wave amplitude, I actually probe these type of models from the bottom up, where I probe the big F first, which is contrary to what you'd think about for traditional ALP searches, where, of course, if you're looking for them coupling to photons, you would probe the stronger couplings first, or smaller F. So in some sense, this type of model is a complementary search, where you probe from the bottom instead of the top. There is of course, many of you may have heard, there was a signal observed by the nanograv experiment, which it's shown here in these gray violins. So it's roughly like a signal which is, of order 10 to -9 in amplitude and consistent with flat or maybe some slight negative slope. If you want to attribute this type of signal to Axion from this type of model, then we just checked briefly what you would need. So you need a Axion mass of roughly 10 to -13 eV, and you need F even larger than we were taking in the benchmark points that I showed you before. And with this big of F, you're really, like the preferred region here is really living on the boundary of what's allowed for N effective, because I produce a lot of this dark photon. So I always have to check this. So in principle, you can do it, but this best fit point is really close to the N effective bound. And you need roughly 10 to -5 suppression of the relic abundance in order to not overclose the universe. So this is a point I'll come back to in just a few slides. But just as a point of what you would need, this is what you would need. Okay, and then I had this really interesting feature where my peak of my spectrum is completely chiral. So this is obviously something that I want to be able to probe, because it's a distinguishing factor for this type of model. Now, it's another question whether I actually can probe it, because I'm dealing with planar detectors like LISA or Einstein telescope. So one option is to build a second version, and then I have 2 different planes, and I can break planarity. The other option is that actually the common wisdom that planar detectors can't measure the polarization of gravitational wave background only applies to an isotropic gravitational wave background. So if I have some way to break isotropy, then I can also, measuring the polarization also becomes possible. So luckily, we do have a built-in way to do this, which is that if we have LISA or Einstein telescope, these are all part of our solar system, which are moving with respect to the cosmic reference frame in which the gravitational wave signal was emitted. So this naturally gives you a dipolar anisotropy in the gravitational wave background. It's exactly the same physics as what gives you the CMB dipole. So if I have no boosting, then I can't tell whether a left polarized gravitational wave is really coming from the left, or if it's just a right polarized gravitational wave coming from the other direction. So they both create the same response in my detector. But now if I boost this system, I have information on the direction of the wave, because from one direction the wave is blue shifted, and the other direction it's red shifted. So now I actually know what direction my wave is coming from, which makes the detector response sensitive to chirality. But of course, this effect has to decouple when the velocity vanishes. So I have to pay a suppression factor of order 10 to -3, which is our peculiar velocity. This has to be paid somewhere. So in the end, you pay it linearly so this is SNR squared, you pay it linearly in the SNR. So here the red, for example, is the LISA signal it's our detection limit for unpolarized, where you're not sensitive to polarization. And if you want to detect polarization, you have some smaller subregion where you're sensitive. And same thing for Einstein telescope. So these dash curves here are the subregion of LISA and Einstein telescope, where we'd be able to detect the polarization of the signal and potentially discriminate against other models. Some more on the model cosmology. I haven't talked much about it because in the beginning, I assumed this dark photon can be massless, or it's just massless for simplicity. Actually, the story goes through completely as long as the dark photon is lighter than the axion. So I can actually give this dark photon a mass. And then depending on the parameters of the theory, I can either have the axion abundance remaining be dark matter, or I could have the dark photon itself be dark matter. So this exact mechanism was noticed by these 4 papers at the same time as a viable way to produce vector dark matter, which is actually not so easy to produce in general. So any new way to produce vector dark matter is interesting. And here in green, I show the region where you can have, for some value of the dark photon mass, you can have the dark photon be all dark matter as long as you are able to sufficiently suppress the axion contribution. And at some point, the dark photon becomes too light, so then you run into warm dark matter bounds. And below that, the dark photon is behaving like radiation degree of freedom, so eventually you hit an effective bound. So those are the 2 main cosmological constraints on the dark photon. And coming to the sort of elephant in the room, there's in general, you need a huge suppression of the Rayleigh abundance of the axion field, because we're talking about very large decay constants, 10 to the 17 GeV. And in order to have acceptable cosmology, aka not overclose the universe, I need to really have this process be truly efficient enough to suppress by 5 or 10 orders of magnitude. So this black dot here is the benchmark point which can explain nanograv. And to get there, I need 10 to minus 5 suppression in the Rayleigh abundance. And to get to the LISA region where I can do all these nice things like potentially probe polarization, I need even more 10 to minus 10 suppression. And everything here I've done has been in the linear analysis. So if I really want to know the final answer to this question, I need to take into account this backscattering where dark photons can backscatter into axions and induce anisotropies in the axion field as well. So we're in the final stages of doing this on the lattice. This is an older plot, but newer, higher resolution plots mainly confirm the same thing. This is, so what am I showing here? The black line is if you do nothing in some sense, it's just standard misalignment with no particle production. The blue line is the result you'd get from the lattice analysis, and the purple line is what you would get from the linear analysis. So according to linear analysis, it seems like you can suppress, by 10 orders of magnitude or so. And that's because you relied on this parametric resonance phase to do most of the suppression of the Rayleigh abundance. Now, the tachyonic phase, which is this early part, like up to A of order 10 or so, this part actually is more or less intact. It agrees roughly with the linear analysis. It's just that this phase out here, the parametric resonance part, this is essentially gone. And this is not so unexpected because what you have is the dark photon backscattering. It destroys the axion condensate. So you lose this coherent enhancement of the zero momentum axion condensate resonating with the dark photon modes. So this is actually not so surprising. I think we understand why this happens. In the end, the lattice result suggests you can suppress only by 10 to minus 2, maybe 10 to minus 3. But because the tachyonic phase is mostly intact, and that was the part that dominates the gravitational wave signal, our gravitational wave spectrum mostly survives. There are 2 main differences now. We have because we have inhomogeneities in the axion field now as well, the axion itself can act as a source of, it sources the anisotropic part of the stress energy tensor. So there's some scalar contribution to the stress energy that we're now including. And also, before the peak sort of ended around momentum of order like 50 or so in terms of KNM. And you see there's the high momentum part of the spectrum is a bit more extended now. And we think this is because you have these 2-to-1 processes, which give you more enhancement in the high momentum part of the gravitational spectrum. But you see, at least in terms of amplitude and rough peak placement, this green cross, which shows our naive dimensional analysis estimate again, it still more or less works. So the shape is a bit different, but the main story for the gravitational spectrum survives. Okay. So if we live with the fact that we can only get 10⁻²? Suppression on the lattice, then really I only have this. My parameter space is cut down to just the tip of SKA here, which is viable in terms of not overclosing the universe. So if I want to open up this interesting region with LISA, where I can probe polarization, I need some new ideas to suppress the Axion relic abundance. And the two ones I'm showing here both center around the same philosophy, which is you need to find some way to reduce the Axion mass after it's done its thing producing gravitational waves. So one thing you can do is you can do some type of monodromy thing where the Axion potential is really not one cosine, but it's two cosines with hierarchical scales. So in the beginning of the process, you just see the big wiggle of cosine, but as the amplitude damps down, you start to resolve another smaller small wiggles of another cosine, and you have to tune them a little bit to get a approximate cancellation of the Axion mass at the bottom. So this is one possibility if you're willing to do this tuning. Okay, it's a bit artificial, but I can do it. And the other thing would be that we're thinking along the lines of is if I can somehow, if this Axion potential is generated by some QCD-like sector, dark QCD-like sector, with some dark quarks that became massive, but somehow now I could think of some inverse phase transition where the dark quarks become massless again, and then this Axion potential would disappear, and the Axion would become massless. So this is another direction that could potentially work. Right now, these are both directions we're thinking. New ideas are also very welcome. But actually, there's one other thing which I can do automatically without sort of doing these more crazy ideas. I can just look. It seems like my relic abundance problem is less acute for lower masses. So what happens if I go below the SKA range, for example? Well, in this range, there's really only one thing that can be used to probe gravitational waves, which is these so-called spectral distortions of the CMB. And these guys, I'm still learning completely about these, but the main idea is that you have gravitational waves, which are tensor perturbations that also source just gravitationally perturbations in the photon fluid. And because these perturbations are massless, they mainly dissipate by free streaming effects. So you can distort the CMB over a large range of scales because of this free streaming. And in principle, there's important part is there's 6 decades or so where these spectral distortion experiments would be sensitive where there's no other probe. So you have Planck, and then you have SKA or other pulsar timing arrays. But in between, there's this desert, which only spectral distortions seem to be able to probe. Now, these authors were nice enough to actually take our model with our fit template for the gravitational wave spectrum and do the analysis in terms of detectability. So it's again this instead of inverse of F, now it's just directly F and Axion mass. And here this mu is the magnitude of the spectral distortion. And these dash curves are the detectability curves for each experiment. None of these experiments are actually flying yet. This PIXI experiment, as I understand it, is a mature design, which is waiting to be approved, and potentially maybe 2025 or something like that, it could fly, but it's still unclear. However, for us, these spectral distortion experiments are quite nice because I can probe this region here of my parameter space, and this dashed black line is the one I'd expect to get the right relic abundance for Axion for ALP dark matter if I have 2 orders of magnitude of suppression due to the particle production. And it goes right through this region that would be probed by the spectral distortion experiments. So here you don't have to do anything crazy with additional suppression mechanisms. This region sort of just works naturally. So this region is very interesting for us. So just to conclude, I've talked about a model where you have some axion dynamics in the early universe. And if you're coupled to a light dark photon, there's a possibility to generate a gravitational wave spectrum. And it has interesting features that it's peaked near the mass, and it's detectable in principle by future gravitational wave experiments if you have a big decay constant. And you have a smoking gun feature of the model is that you have this highly polarized peak. So if you have a detector which can probe polarization, this is a distinguishing feature for the model. And yeah, it wasn't what we originally thinking about when we set out, but now it seems like actually this low mass region that can be probed by spectral distortion experiments, where the cosmology sort of works, is maybe the best probe of the model. If you want to go to the higher mass region, like LISA mass region, where you can really have this nice probe of polarization, then yeah, you need to have some additional suppression mechanism, which we're currently still investigating. So yeah, I think that's basically it.
Thank you, Benjamin. Are there any questions or comments?
I have one. Yeah, this is Philip from Daisy. I noticed that yesterday. Yeah, hi. I noticed yesterday a Japanese group put up a lattice study that appeared to study your exact model. I don't know if you.
Yes.
I don't know if you saw that.
Yes.
Could you comment on what they found?
Yeah, I think
Like how it compares to yours?
Yeah, we're currently, like I said, in the final stages of our lattice simulation as well, and we, I think, more or less roughly agree with them. I think there's an effect which I didn't mention, which is that here I showed the spectrum for alpha roughly 50. If you go to even larger values of alpha, the backscattering can become efficient early on in the tachyonic phase, such that you can actually wash out the polarization. Or even you can have a flip in the polarization where the one which is initially subdominant, actually ends up dominating in the end. And this is really due to the backscattering. So we have a little bit of, I think we find slightly different results for how the polarization scales with alpha. But other than that, I think in terms of suppression of the relic abundance, we more or less agree with them.
Okay, that's nice to see.
Yes.
Okay, thank you.
Sorry.
Hi, Benjamin. I have Ricardo Ferreira here.
Hi.
I have a question also. So if you could go back to your to the expression for the gravitational wave abundance. So yeah, like the one you just passed, yeah. So I'm a bit confused here because so when F becomes very large or when alpha becomes very small, the axion decouples from the dark photon, right? Yeah. So
yeah, yes.
So and then I would expect that no signal. So why does that is not showing up?
Because this is an approximate. You can't really take the alpha goes to zero limit here because we've already assumed like in deriving this relation, it's already approximation where we assume we have alpha like order 10 to 100. So it really only works in this regime.
And for F the same. So for F very large, I would also expect to have a suppression of the signal.
The non-decoupling behavior there occurs because you're assuming theta is order 1. So you're assuming, like, as you take f larger, the amplitude, initial Axion field amplitude that you have also increases. So yeah, in that sense, you're increasing the energy budget you have for the gravitational wave signal, right? So there, it's really it doesn't decouple.
Sorry,
yeah, go ahead. Sorry.
Because I mean, the coupling to photons depends on is basically the Axion velocity over f, right? So
yes.
so if f is very large, it decouples, but it's not very sensitive to the.
But the Axion velocity
that theta also increases. Okay.
Yeah, the Axion velocity itself also scales with f, so somehow the effect cancels there. That's the point. And it is tied to this, to theta always being 1. If you adjust theta, this doesn't go through. Yeah.
Okay. Thanks.
Yep.
Similar question is, so in your sample parameter points, alpha is always assumed around 50. So what determines the value of alpha?
So alpha, in principle, let me show you. I think I have some slide. Yeah. So in principle, like there's alpha, this alpha tilde is what we're always talking about. And it's related to the fundamental U1X coupling like this, where you have some loop factor suppression and also some, here I put it as n, where it could be like the number of species in the loop, but also there's some anomaly coefficient where the representation of whatever is running in the loop could enter. And in principle, yeah, here it's not, I mean, you could simply take number of degrees of freedom in the loop large, which is not necessarily the best solution, but in the end, if you really want to get alpha large in a sort of a natural way, you need some, like some clockworking type mechanism where you have a series of, like, say, Strom groups that are connected by link fields with each one of those.
My question is, what's the phenomenological reason to have such a large alpha? Why do we need
the phenomenological reason for us is we want a big gravitational wave signal. This is that's
so if alpha is order 1, then we cannot obtain the gravitational wave signal.
Correct.
Observable.
Yes, correct.
So what condition keeps that? In your previous education, I can see that.
It's because, okay, let me go back here. Yeah, you can see it because, yeah, let me look here. It's really, okay, let me go back here. Yeah, so the modes that are tachyonic are really those with k less than alpha theta times m, right? So if alpha is order 1, theta is order 1, then it's the modes k less than m. But then you're somehow comparing this to the to the oscillation time, and in order for the modes to grow efficiently within one oscillation time, you need some momenta which are higher than m, so that they grow faster than the oscillation time, right? So you have a cutoff there, which is set by the period of the Axion oscillation. So you don't efficiently pump the modes if alpha is order 1, basically. Does that make sense?
Yeah. Actually, I have another question. So here, what's the problem if we consider tachyonic photon production instead of dark photon?
There's no, in principle, there's no problem. The problem again comes because I want gravitational waves. So in the case of the standard model photon, what happens is you always have coupling to light fermions, electrons, for example. And there, once you start to tachyonically produce the standard model photon, you also pair produce electrons, and there's a thermal mass induced for the dark photon, or sorry, for the standard model photon. And this large positive thermal mass kills the tachyon. So this process sort of back reacts on itself and shuts off in the case of standard model photon, where you have light degrees of freedom, light fermions. So mathematically, there's nothing wrong. It's just gravitation. If you want a gravitational wave signal, yeah, you can't have this. You can't generate this thermal mass. That's why we went to the dark photon setup.
Okay, thank you.
I have several questions. Do we expect strong gravitational wave signals if we consider dark non-abelian gauge group?
Again, it's a similar. There's also a mechanism there because if you have non-abelian gauge group, then you have self-interaction of the gauge boson, and this self-interaction again sort of generates they call it, in that case, it's like a magnetic mass, but the effect is the same where you have some positive mass for the gauge field generated that shuts off the tachyon. So again, you can have it a little bit, but it's just not as efficient as the U1 case where you don't get any effective masses generated. Yeah.
I see. And another question is about so in your scenario, you assume gravitational wave production in a radiation-dominated era. So I think the axion energy density is subdominant when the gravitational waves are produced. And but in this case, an advantage is that gravitational waves are not diluted during radiation-dominated era relative to the total energy density. On the other hand, if we consider some axion-like inflaton, then the total energy budget is there is more available energy, but once you produce gravitational waves, it is continuously diluted compared to the background energy density. So if we compare these scenarios, then which is advantageous in the perspective of gravitational wave observation, or do you have any other?
Which is advantageous in terms of what? Sorry, I missed the
gravitational wave observations.
Well, I don't know exactly with the case where the axion drives a period of inflation, but there I think you need to, people study like these axion inflation models where you do produce a gravitational wave signal on top of what you would get ordinarily from usual inflationary fluctuations. And somehow there, like roughly the idea is that since the production of the gravitational wave signal is exponential and also the dilution is exponential, there's a rough cancellation where you end up getting some non-vanishing thing. But I haven't studied that in detail myself, and you'd have to, for sure, in this case where I'm doing it after inflation, find another mechanism to reheat the universe, right? So yeah, that's my rough comment. I don't know exactly how it works, but
I see.
It's another regime you can study. I just we didn't look at that.
Are there any further questions or comments? If not, let's thank Benjamin again. So we have 3 discussion sessions. So if you have any questions or comments to either of the speakers, then you can ask.
Okay, if there's no further questions, then it may be time to close this workshop. So I think it was quite interesting and instructive workshop highlighting the recently important progress on axion-like particle detection and possible astrophysical signatures. So I'd like to thank all the speakers and participants for your contributions and participation. So we hope to see you next year again. And thank you. That's it.
Thanks.
Thank you.
Thank you.